Let us start the displacement analysis of quick return mechanism. These mechanisms are used in shaping machine. So quick return mechanisms are used in shaping machine. So first, let me denote the link numbers and kinematic pairs. Fixed links are denoted by 1. This is link number 2, that is the crank or bull gear, which is rotating in counterclockwise direction with an uniform velocity, uniform angular velocity omega 2, that is shown in the diagram. Now the slider is 3, slider is link number 3, and this oscillatory link is link number 4, this is link number 5, and this slider is link number 6 or tool holder. So this is the tool here. Now this revolute pair is denoted by O2 at it connects link 2. This is O4. This revolute pair is A. This revolute pair is B, and this revolute pair is C. So there are 5 revolute pairs and 2 prismatic pair, that is this is one prismatic pair here between 3 and 4, and between 6 and 1 there is another prismatic pair, so 2p. So there are 6 links in each 6, 5 revolute pairs and 2 prismatic pairs. Now let me show you a model of quick return mechanism. This is a model of quick return mechanism. O2, O4 is the fixed link. Now this red link is the crank or bull gear. This green color link is the slider. And this blue color link is the oscillatory link, that is link number 4. Red link is link number 2, green link, that is the slider, is link number 3, and blue color link is the link number 4. This yellow color link is the link number 5, which connects link 4 and link 6. This slider is link 6. Green color slider, this slider is link 6. Now continuous rotation of crank, that is the red link or link number 2, produces to and fro rectilinear oscillation of this link number 6, and which is nothing but the tool holder. This link number 6 is nothing but the tool holder. Now let us see that this is crank is rotating in counterclockwise direction with an uniform speed, and this slider reaches at the extreme points, that is now it is at extreme left position when this oscillatory links is tangent to this circle. This circle is nothing but generated by point A, that is this revolute pair here. This circle is generated by this revolute pair, and this slider, that is link number 6 or the tool holder, reaches the extreme positions when link 4 is tangent to this circle. Here it reaches the extreme position. Now from this position it will back to right extreme positions. Now let us see here, this is the position of crank. So this is the position of crank. This is the position of crank when the tool holder is at extreme right. Now from this it comes to here when it reaches to extreme left. So this is one stroke. This is one stroke which is called forward stroke. This stroke is forward stroke. So this total angle is called forward angle, and this angle is theta r, which is return angle. So here theta f is greater than theta r, that's why the tool holder or link 6 moves faster during return stroke. So this is now from this forward stroke starts, forward stroke completes here. Now this is return, and return stroke is faster compared to forward stroke. This is a kinematic diagram of a quick return mechanism. And the objective of displacement analysis is to determine the stroke, and quick return ratio of the mechanism. Here, link number 2 is the input link, and we have already mentioned that link 2 is rotating in counterclockwise direction with an uniform speed, or uniform angular speed omega 2. Counterclockwise direction and uniform angular speed omega 2. And link 2 is hinged at revolute pair O2. So link 2 has a pure rotation about the revolute pair O2. So the point A moves on a circle. So point A moves on a circle, and that circle has center O2 and radius equal to O2A. That is the length of link 2. So first let me draw the circle. So let me draw the circle first. So this is the circle on which point A moves, and this circle has center O2 and radius equal to O2A. And let me denote this circle by KA. This circle is KA. Now to determine stroke, we have to locate two extreme positions of point C, because stroke is nothing but the distance between two extreme positions of point C, that is the right extreme position and left extreme position. Let us consider the right extreme position is CR and left extreme position is CL. So when point C at extreme right, that is at CR, the oscillatory link, that is link number 4, will be tangent to this circle KA. So first let me draw a tangent to the circle KA from point O4. So let me draw. So this is tangent to circle KA from center O4, and length of the tangent will be equal to O4B. That is the length of link number 4. And this point denotes BR, that is the extreme right position of point B. Now let me draw the axis of the slider. Let me draw the axis of the slider. This is the axis of the slider 6. Now to locate CR, we have to draw an arc from center BR, with radius equal to BC. BC is the length of link number 5. So we'll draw an arc from center BR with length BC, with radius BC, and that cuts the axis of the slider here, and that is nothing but CR. So this denotes or this locates CR. So this is the position of CR. So we have located CR and this is link number 5. So at extreme right instant, the mechanism will be like this. This point is AR. So this is the slider. This is AR. So O2AR, O4BR and BR to CR. So this is the instant when point C is at extreme right. Now similarly, by similar drawing construction, we can locate CL also. So to locate CL, we'll draw a tangent to this circle K from point O4 and this point denotes BL, this point denotes BL, and from BL to CL. So this is CL. So these are two extreme positions of point C, and this point denotes AL. So these are two extreme positions of point C. Now what is stroke? Stroke is CRCL. That is, this distance is the stroke. This distance is the stroke. And what is quick return ratio? Quick return ratio is, we know that time taken by forward stroke divided by time taken by return stroke. We know that stroke is CRCL, that is the distance between two extreme positions of point C. Now what is forward stroke and what is return stroke? Let me explain. We have considered that link 2 here is rotating in counterclockwise direction, with uniform speed omega 2. Now let us start from extreme right position of C, that is CR. So where is my mechanism? At this instant, my mechanism at here. O2AR is the crank. This is link number 4, O4BR. Then BRCR is link number 5 and this slider is link number 6. So from this instant, say when crank is at O2AR and crank starts rotating in counterclockwise direction, what happens? This slider starts moving in left hand direction. So this slider starts moving in left hand direction and it will reach to CL when this crank will reach from O2AR to O2AL, and that completes the forward motion. So this motion is known as forward motion. So forward motion means slider moves from CR to CL, slider moves from CR to CL or tool holder moves from CR to CL, and corresponding motion of the crank is what? Crank moves from O to AR, O to AR to O to AL. Crank moves from O to AR to O to AL. After that, what happens? After that, from O to AL, from O to AL, cranks starts further moving in counterclockwise direction, and this slider will back because this is the extreme position. The slider cannot move beyond CL. So slider starts return from CL and it will goes to CR, and the corresponding motion of the crank is O to AL to O to AR. So O to AL to O to AR. Now this is the return motion. This is return. In return, slider moves from CL to CR and crank moves from O to AL to O to AR. And let me denote now this angle, this total angle, that is O to AR to O to AL by theta F, and O to AL, O to AL to O to AR by theta R. So forward motion, in forward motion, slider moves from CR to CL in left hand direction. So this is forward motion. And return motion, in return, slider moves from CL to CR. So this is forward motion and this is return motion. And during forward motion, crank travels from O to AR to O to AL, which is denoted by theta F, and during return, crank moves from O to AL to O to AR, which is denoted by theta R. Now we have considered that crank is rotating with uniform speed omega 2. So what is time taken by forward stroke? Because we know the motion of the crank during forward stroke. So the angle traveled by the crank is theta F. So this is the angle traveled divided by the speed is the time taken by forward stroke. Similarly, time taken by return stroke will be theta R by omega 2. That is theta F by theta R. And the summation of theta F and theta R is 360 degree. So we can write 360 degree minus theta R divided by theta R. So this is the expression of quick return ratio. So this is the expression of quick return ratio. Now let me give you an expression of theta R from this diagram. So theta R, that is return angle traveled by the crank, which is nothing but the angle AL O2 AR. This angle AL O2 AR. Now this angle is nothing but half of theta R. So this is theta R by 2. And O4BR is tangent to circle KA. So this is 90 degree. This angle is 90 degree. Similarly, this is also 90 degree. So triangle O4 O2 AR is a right angle triangle. So this triangle is a right angle triangle because this angle is 90 degree. So we can write cos of theta R by 2. Cos of theta R by 2 is what? This angle is theta R by 2. So cos of theta R by 2 is O2 AR by O4 O2. O2AR is nothing but O2A divided by O4 O2. So O2A is the length of the crank and O4 O2 is the length of the fixed length. That is, theta r or theta r by 2 is function of the length of crank and length of the fixed length. So from this we can calculate theta r by 2. If we put the value of theta r here, that is, if we can calculate theta r by 2, we can get value of theta r. So put here the value of theta r and you will get the quick return ratio easily. We have derived the expression of quick return ratio. Now let us derive the expression of stroke, that is CRCL, from this diagram. To do that, first let us join BL BR by a line, and the midpoint of BR BL is D, and extension of O4 O2 cuts BL BR is at point D also, because B O4 BR and O4 BL are symmetric about the center line O4 O2. So D is the midpoint between BL and BR. So DBR is nothing but DBL. And let us consider this distance. This distance is E. So similarly, this will be also E. This will be also E. So CRCL, that is the stroke, which is nothing but DBR minus E plus DBL plus E. So EE cancelled, that is DBR plus DBL. So DBR plus DBL, which is nothing but 2 DBR, as DBR equal to DBL. Now what is the expression of DBR? This angle is theta r by 2. So this angle is 90 degree minus theta r by 2, because we have seen that this angle is 90 degree and triangle O4 O2 AR is a right angled triangle. So angle O2 O4 AR is 90 degree minus theta r by 2. So DBR is what? DBR is O4 BR sine of this angle, that is 90 degree minus theta r by 2, and which is O4 BR cos theta r by 2. So CRCL, that is the stroke of the mechanism, is 2 into O4 BR cos of theta r by 2. So this is the expression of the stroke. Now we can extend it to O4 BR or O4 B into, we have already determined that cos theta r by 2 is O2A divided by O4 O2. So stroke depends on length of the crank. O2A is length of the crank. Now if we want to reduce the stroke, that is, we want to reduce the stroke for a smaller length job, then what to do? We have to reduce the length of the crank. That is, we have to reduce the length of O2A, because length of fixed link is always fixed, and length of oscillating link is also fixed. O4BR or O4B is also fixed. So the conventional way to reduce stroke is to reduce the crank length. That is, we have to reduce O2A. But there is a problem associated with this, because this machine is not efficient for shorter stroke length. Why? Let me explain through a diagram. We have derived the expression of quick return ratio and stroke of a quick return mechanism. Now the question is that if we want to reduce the stroke for a small job, then what happens to the value of quick return ratio of a quick return mechanism? The conventional way to reduce the stroke is to reduce the length of the crank, that is O2A. So we have to reduce O2A, that is the crank length. And let us see what happens to the value of quick return ratio if we reduce O2A. So in this figure, this is the circle, the long circle or big circle, that is the circle generated by point A. This is point A, which is a long crank. So this is for long crank. And this is the circle, the inner circle, that is KA short. This is circle generated by shorter crank. Now let us draw the orientation of oscillating link, that is link number 4, for both the crank when C at extreme right. So let us draw the tangents. So this is one orientation, and another orientation will be like this. So this is BR for long crank, and this is, let us consider, this is BR for shorter crank. So these are two tangents. Now what is the value of theta r by 2 for each crank? Let us see. This is for shorter crank and this is for longer crank. So we see that if we reduce O2A, the value of O2A, then we have seen that the value of theta r by 2 increased, because this value is theta r by 2 for long crank, whereas theta r by 2 increased here. Here theta r by 2 increased for a shorter crank. So this is theta r by 2 for short crank. So we have seen that if we reduce O2A, the value of theta r by 2 increases. So if theta r by 2 increases, then from this expression we can understand that the value of QRR reduces. That is, if we want to reduce stroke of a quick return mechanism, if we want to reduce the stroke, then we have to reduce O2A. If we reduce O2A, then the value of theta r by 2 increases. If theta r by 2 increases, then value of QRR reduces. So value of QRR reduces, which is not desirable. This is not desirable. Why not desirable? The value of QRR, lesser value of QRR indicates that the return speed is not faster compared to forward speed. And in return motion, the machine has no work. In forward motion, cutting operation takes place. In return motion, there is no work. So the machine has to return in faster speed. If that not occurs, that indicates a lesser QRR indicates that production rate is low or production rate is not high. Production rate is not good. So the machine is not efficient. So this is the drawback of a quick return mechanism for small stroke length. So this is not suitable for small stroke length like slotting machine. So this problem has been addressed, or this problem has been solved in Whitworth quick return mechanism, where quick return ratio is independent of stroke length, and in next lecture we will see that in Whitworth quick return mechanism the quick return ratio is independent of stroke length. Let us solve the problem which has been asked in GATE 2009. The quick return ratio of the mechanism is 2:1, that is quick return ratio is 2. If the radius of the crank O1P, radius of the crank, it is given 125 mm. The distance D, this is the distance D between crank center, that is O1, to the lever pivot center point should be what? Lever center point is O2, that is we have to calculate the length of the fixed link O2 O1. So quick return ratio is given, quick return ratio is 2:1, and we know that quick return ratio is theta f by theta r, and we also know that theta f plus theta r is 360 degree. So if this is equation 1 and this is equation 2, and solving 1 and 2, we can easily find that theta r is 120 degree. Then what is theta r by 2? Theta r by 2 is 60 degree. So here, to locate theta r by 2, what we have to do? We have to draw a circle at center O1, and radius O1P. So this is the circle, and the oscillating link or the lever, that is O2P, will be tangent to this, and we know that this angle, as this is tangent, so this is 90 degree, and this angle is theta r by 2. So from triangle, if this is point PR, so from triangle O2 O1 PR, we can write cos of theta r by 2 is O1P by D. D is 1 O2. So cos theta r by 2 is, so from this equation we can write cos of 60 degree, as theta r by 2 is 60 degree, that is 1P is given 125 divided by D. That implies cos 60 degree is half, equal to 125 by D. If we solve this, we can easily get the value of D. D will be 250 mm. So we have easily find that D is 250 mm. So the answer is 250 mm. We are ending our session here. Thank you.